Hey guys, in this video I will present a solution to USA team selection test for the IMO 2014 problem 4. Firstly, we'll take a look at the statement. Let n be a positive even integer and let c1, c2 up to cn-1 be real numbers, such that the sum going from I equal to 1 up to n-1 of the absolute value of ci-1 is less than 1. We shall prove that the polynomial p of x, which is defined to be equal to 2 times x to the power of n minus cn-1 x to the power of n-1 plus cn-2 x to the power of n-2 minus so on, alternating signs up to minus c1 x to the power of 1 plus 2 has no real roots. This condition tells us that ci minus 1 has absolute value less than 1 because each of those terms is at least 0. Therefore, ci must be greater than 0. Now we can take a look at what this tells us about each summand for p of x if we plug in some value for x. So the ith summand for 1 is less than or equal to I less than or equal to n-1, then the ith summand of p of x is nothing but negative 1 to the power of I times ci times x to the I. So we immediately see that this is greater than or equal to 0 for x less than or equal to 0, because we can see that this is equal to ci times negative x to the power of I. So each of these inner summands of p of x evaluated at x less than or equal to 0 is non-negative, but since 2 is positive, it follows that p of x is also positive for non-positive x, and therefore in this case we are done. So from now on we will only consider positive x in our question. Now we have already used our given condition once. If we take a look at what it tells us, is that all of the ci are really quite close to the value 1, or rather that they can't all be far away from 1. Therefore, our polynomial p of x is quite similar to the polynomial q of x, which we define to be equal to 2 times x to the n minus x to the n-1 plus x to the n-2 up to minus x to the 1 plus 2. And q of x is equal to x to the n plus 1 plus x to the n plus 1 divided by x plus 1, because if we imagine this to be a 1 and this also to be a 1, which we can do by subtracting x to the n plus 1, then this is a geometric series with factor negative x. Now q of x is a positive polynomial, and for x greater than 0 this is particularly easy to see because this is positive and every other summand is also positive. So this is greater than 0 and thus has no roots x greater than 0. Now this is not quite what we wanted to prove, but already quite nice, because we have said that p of x is at least similar to q of x in terms of its coefficients. To capture this similarity, we will define a third polynomial, let's call it delta of x, by p of x minus q of x. Now if we can see that delta of x can be large enough to make up for the fact that q of x is quite positive, then we will also be able to conclude that p of x can't take the values less than or equal to 0 and therefore doesn't have roots either. Now delta of x we can evaluate, and it is equal to 1 minus cn minus 1 x to the power of n minus 1 minus 1 minus cn minus 2 x to the power of n minus 2 plus and with alternating signs in this sum again, and we finish with the term 1 minus c1 x to the power of 1. This is a good reason to introduce new variables. In particular, we will define di to be equal to 1 minus ci. This is quite nice because then our condition also tells us many things about the di, in particular one thing, that their sum of absolute values going from I is equal to 1 up to n minus 1 is less than 1. And furthermore, delta of x is nothing but little delta n minus 1 times x to the power of n minus 1 minus delta n minus 2 x to the power of n minus 2 up to delta 1 x to the power of 1. Now let's do a small recap of the ideas which we have implemented so far. We realized that our condition tells us that the ci are quite similar to the value 1. Therefore, the polynomial p of x is in coefficients in the same way quite similar to the polynomial q of x. We also noted that q of x is always positive. Now we introduced a new polynomial delta of x, and at this point it would be enough to prove that the absolute value of delta of x is smaller than q of x, because in this case, by the triangle inequality, this would be enough to show that p of x is also always positive. So the takeaway from this is that we want to consider the absolute value of delta of x. Now, I am not going to write all of this down again, but rather I'm going to do one more step immediately, because we want to bound this absolute value from above, and we can use the triangle inequality which tells us that the absolute value of delta of x is less than or equal to the absolute value of the sum going from I equal to 1 up to n minus 1 of the absolute value of di times x to the power of I, where x is of course positive. We already have information about the sum of absolute values of di, namely that it is less than 1. In this case, we also have a term x to the power of I within each summed. But we note that if x is greater than 1, then the largest of these terms, x to the power of I, is going to be exactly x to the power of n minus 1. If x is less than 1, then the largest is going to be x to the power of 1. And for x equals to 1, there's equality, of course. Now, this tells us that no matter the choice of x, the largest term is never going to be for some I between 1 or n minus 1. Therefore, to maximize this value of this sum, it would never make sense to put the weight of the delta I to the middle. This motivates us to bound x to the power of I by x to the power of 1 and x to the power of n minus 1. In particular, this sum is less than or equal to the sum going from I is equal to 1 up to n minus 1 of the absolute value of delta I times the maximum of x to the power of 1 and x to the power of n minus 1. And this is really nice. So basically what this does, but maybe in a different way, is we put the weight to the outside, because this is nothing else than putting all of these delta I into the corresponding largest value of x to the power of I. Now this we can evaluate nicely, or rather say that, well, because each of those is equal, we can pull it out of the sum, and therefore we can use the fact that this sum is less than 1. So all of this is less than the maximum of x to the power of 1 and x to the power of n minus 1. Originally, we wanted to compare the absolute value of delta of x with the polynomial q of x. Here we see that we have the sum x to the power of n plus 1. And here we have an x to the power of n, 1, and x to the power of n minus 1. I'm going to do one step that you might try when solving this on paper, and maybe it is going to work, but maybe not. But in this case, works out nicely, because we can just say, because those are nicer numbers, that this maximum is less than or equal to the maximum of x to the power of 0 and x to the power of n. And this, in turn, is less than or equal to 1 plus x to the power of n, because both terms are non-negative. Originally, we wanted to compare the polynomials p and q. To do that, we introduced delta, which we now have an upper bound of, at least for its absolute value. Therefore, we conclude that p of x, which is just greater than or equal to q of x minus the absolute value of delta of x, because delta of x is the difference between p of x and q of x. Now, all of this is greater than q of x minus 1 plus x to the power of n. We have an explicit form for q of x, and we see that all of this is equal to x to the power of n plus 1 divided by x plus 1, which is clearly greater than or equal to 0. Therefore, p of x is also greater than 0, and we're done.